Welcome everyone. I'm excited to welcome you to our presentation, titled Mass Matter, where physics meet curiosity. Today, we'll explore fascinating insights into the world of mass and matter, and how they connect with our natural curiosity. We'll cover some fundamental concepts, interesting discoveries, and intriguing questions that keep scientists and enthusiasts alike captivated. So, let's get started and dive into this exciting journey together. The universe we observe around us is actually governed by four fundamental forces, and these are the key to understanding everything from the largest galaxies to the tiniest particles. These forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, act like invisible hands, orchestrating the cosmic ballet that has been unfolding since the Big Bang. They are the underlying rules that shape the structure and behavior of the universe. As we explore these forces, you'll see how each one plays a vital role in creating and maintaining the universe we live in. Understanding them is not just about physics, it's about unlocking the mysteries of space itself, helping us to grasp how everything fits together. So, through this journey, we'll see how these forces connect to the broader theme of space science and our quest to understand the cosmos. Gravity is the weakest of the four fundamental forces, yet its reach is truly vast. Its influence extends across infinite distances, which makes it the main architect of the universe's structure. What's fascinating is that gravity is an attractive force between masses. It's what binds planets to their stars and holds entire galaxies together. It also controls the orbits of celestial bodies, guiding their paths through space. Plus, gravity is essential for navigating space, controlling the trajectories of spacecraft and satellites. Now, Einstein's contribution really changed how we think about gravity. Instead of seeing it as just a force, he described it as the curvature of spacetime caused by mass and energy. Think of it like a fabric. Mass creates a well or a dip in this fabric, and objects move along these curves. For example, Earth orbiting the Sun is a perfect illustration of this concept. The Sun's mass creates a kind of well in spacetime, and Earth's orbit is just it moving along this curved path. This idea helps us understand why gravity works the way it does, and connects directly to the overall theme of how gravity shapes our universe. Now, let's explore the electromagnetic force, which is responsible for almost everything we experience in our daily lives, apart from gravity. It acts between electrically charged particles and can cause them to attract or repel each other, depending on their charges. This force plays a crucial role in many phenomena around us. First, let's talk about light and energy. The electromagnetic force powers all forms of electromagnetic radiation, from long-wavelength radio waves to visible light and even gamma rays. This broad spectrum allows us to observe distant cosmic objects, giving us a window into the universe beyond what our eyes can see. Next, consider atomic bonds. The electromagnetic force is what binds electrons to the nuclei of atoms, holding atoms together. It's also what keeps atoms linked together to form molecules, which are the building blocks of everything around us, crucial for life, technology, and materials. Finally, on a cosmic scale, this force creates Earth's magnetic field, acting as a protective shield against solar radiation. It also drives spectacular phenomena like solar flares and the aurora borealis, which are some of the most beautiful displays in nature. All these points highlight how fundamental the electromagnetic force is. It connects the very small to the very large, shaping our universe and our everyday experiences. The strong nuclear force is truly the powerhouse behind atomic nuclei. It's actually the mightiest of all the fundamental forces, about 100 times stronger than electromagnetism, which is pretty incredible. But what's really fascinating is that it only acts at incredibly tiny distances, around 10 to the minus 15 meters, so it's confined to the very heart of the atom. So how does it work? Well, it basically overcomes the electromagnetic repulsion that occurs between protons, since protons are all positively charged and naturally repel each other. Without this force, atomic nuclei wouldn't hold together. Instead, it binds protons and neutrons together, creating stable nuclei. This force is carried by particles called gluons, which act like the glue, hence the name, that hold quarks together inside protons and neutrons. And beyond just holding atoms together, the strong nuclear force powers nuclear fusion, the process that fuels the sun and other stars, giving us the energy that lights and warms our planet. Scientists study this fundamental force through experiments at CERN, where they collide particles at speeds close to the speed of light. These collisions help us understand the very nature of the strong nuclear force and how it governs the building blocks of matter. The weak nuclear force is fascinating because, although it operates on an even smaller scale than the strong force, it is absolutely essential for some of the universe's most important processes. One of its key roles is in particle transformation. Unlike other forces, the weak force has the unique ability to change one type of particle into another. This capability is what drives radioactive decay and allows for the transmutation of elements, which is fundamental in fields like nuclear physics and radiochemistry. Another critical function of the weak force is in solar power. Specifically, it's vital for nuclear fusion happening in the sun's core. During this process, the weak force helps convert protons into neutrons, facilitating the hydrogen to helium fusion that powers our star and, ultimately, life on Earth. Additionally, the weak force is responsible for neutrino production. These neutrinos are nearly massless particles that stream through space in the trillions, and because they barely interact with normal matter, they are incredibly elusive. Studying neutrinos helps us understand processes happening deep inside stars and other cosmic phenomena. An interesting and unique aspect of the weak force is that it violates parity symmetry. This means that it treats left-handed and right-handed particles differently, a property that sets it apart from the other fundamental forces. This asymmetry has profound implications for our understanding of the universe and the laws of physics. Overall, the weak force might be small in scale, but it has a huge impact on the universe's evolution and the processes that make life and stars possible. Let's take a closer look at how the fundamental forces compare in strength and range. Starting with the strong force, it has an incredibly high relative strength, about 1039, but it only acts at extremely short distances, roughly 10 to the minus 15 meters, which is on the scale of atomic nuclei. Next, we have the weak force, which is weaker than the strong force, about 1037 in relative strength, but it operates at even smaller distances, around 10 to the minus 18 meters. Moving on, the electromagnetic force has a relative strength of about 10.2. While it's much weaker than the strong and weak forces, it has an infinite range, meaning it can act over large distances, but it can also be neutralized under certain conditions. Lastly, gravity is by far the weakest, with a relative strength of just 1. However, it also has an infinite range and always attracts, which makes it dominant on cosmic scales. This logarithmic scale really helps us understand the big picture. Despite its weakness, gravity rules at large, cosmic distances, while the strong and weak forces dominate at the atomic and subatomic levels. It's a fascinating reminder of how different forces govern different realms of our universe. Let's look at some real-life examples of gravity in action. First up is gravitational lensing. Massive objects like galaxy clusters can actually bend light from distant sources behind them. This creates cosmic magnifying glasses that allow astronomers to peer deeper into the universe and study its early history. Next, we have black holes, regions where gravity is so intense that nothing, not even light, can escape. The 2019 image of the supermassive black hole in galaxy M87 was a groundbreaking visual confirmation of these extreme gravitational environments. Lastly, gravity plays a crucial role in galactic formation. It drives the collapse of gas clouds into stars and shapes the stunning spiral and elliptical structures we see in galaxies across the cosmos. These examples really highlight how gravity is fundamental to understanding the universe's structure and evolution. Let's look at some real-life examples of the fundamental forces we've been discussing, starting with solar activity. The sun's magnetic fields can create these incredible phenomena like solar flares and coronal mass ejections. These events are not just spectacular to observe, they can actually affect our Earth by disrupting communications and power systems. It's a clear example of how magnetic forces play a crucial role in our near-space environment. Moving on to stellar fusion, this is where the strong and weak nuclear forces come into play. Inside the cores of stars, hydrogen nuclei fuse together, releasing enormous amounts of energy. This process is what makes stars shine for billions of years, providing the light and heat that sustain life on Earth. It's a perfect illustration of how nuclear forces drive the fundamental processes in the universe. Finally, let's consider Earth's magnetic shield. Our planet's magnetic field acts like a protective bubble, deflecting harmful solar radiation and cosmic rays. This magnetic field is generated by the movement of molten iron in Earth's outer core. Without this magnetic shield, life as we know it would be much more vulnerable to space weather hazards. These examples really highlight how electromagnetic and nuclear forces are integral to both the cosmos and our daily lives, tying back to the core theme of how fundamental forces shape our universe. Why understanding forces in space science is so important is because it helps us make sense of the universe around us. When we look at cosmic applications, we see that these forces explain how stars, planets, and galaxies form and change over time. This knowledge allows us to predict cosmic events like supernovae, which are these huge stellar explosions, or black hole mergers, which are some of the most energetic events in the universe. It also gives us insights into the very origin and ultimate fate of the universe itself. On the practical side, understanding these forces is crucial for things we rely on daily, like GPS systems and satellite communications. They enable precise navigation and reliable communication across the globe. Space exploration also depends heavily on gravitational assists, where spacecraft use planetary gravity to boost their speed and save fuel. And beyond space itself, the understanding of forces has led to technological advancements that impact many fields, like nuclear power, which relies on nuclear forces, or medical imaging techniques that have revolutionized healthcare. So, in essence, grasping these forces not only deepens our understanding of the cosmos, but also drives innovation and technology that affect our everyday lives. So when we talk about current research and unification efforts in physics, we're really aiming for that ultimate goal, what many call the Holy Grail. It's about combining all four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, elegant theory. Imagine a framework that could explain everything from the moments right after the Big Bang to the mysterious nature of black holes. That's the big picture we're working towards. Now, there are several unification theories that scientists are exploring. One of the most well-known is string theory. It suggests that rather than point-like particles, everything is made up of tiny vibrating strings. These vibrations determine the particle's properties. Then, we have M theory, which is an extension of string theory. It proposes these strings actually exist in an 11-dimensional universe, adding more complexity but potentially bringing us closer to a unified picture. Another interesting approach is loop quantum gravity. Instead of strings, it suggests that space and time themselves are quantized. That means space isn't smooth, but made up of tiny, discrete chunks, which could help us understand gravity at the quantum level. Besides these theories, there are space-based experiments making huge strides. The alpha magnetic spectrometer on the ISS, for example, is studying cosmic rays and antimatter to look for clues about the universe's origins. LISA, the Laser Interferometer Space Antenna, is designed to detect gravitational waves from massive cosmic events, giving us new ways to observe the universe. And then there's the James Webb Space Telescope, which is peering back in time to observe the earliest galaxies and stars, helping us understand the universe's infancy. All these efforts, both theoretical and experimental, are interconnected. They push us closer to unification, bringing us nearer to understanding the fundamental fabric of reality. Now, let's delve into the concept of force carriers, often called messengers of interaction. Each fundamental force in nature operates through the exchange of specific particles that mediate their interactions. For example, the electromagnetic force uses photons as its messenger particles. These photons are responsible for all electromagnetic phenomena you encounter, from the light we see to radio waves, carrying electromagnetic energy between charged particles. Moving on, the strong nuclear force, which holds atomic nuclei together, is mediated by gluons. Think of gluons as the glue that binds quarks inside protons and neutrons, ensuring atomic nuclei stay stable despite the electrostatic repulsion between positively charged protons. Then we have the weak nuclear force, which is responsible for certain types of particle transformations, such as radioactive decay. This force is mediated by W and Z bosons, which play a crucial role in processes like nuclear fusion in stars. They enable particles to change identities under specific conditions. Lastly, there's the hypothetical graviton. It's predicted to be the quantum particle responsible for mediating gravity, much like photons do for electromagnetism. Although gravitons haven't been observed yet, they are a key part of our attempts to unify gravity with quantum mechanics. To sum up, these force carriers are essential because they explain how particles communicate and interact. Photons handle electromagnetic interactions, gluons keep atomic nuclei intact, W and Z bosons facilitate weak interactions, and the graviton, if it exists, would be the messenger of gravity. Understanding these particles helps us grasp the fundamental forces that shape our universe. Did you know that while gravity is responsible for shaping the largest structures in the universe, it is actually incredibly weak? In fact, a small magnet can easily overcome Earth's gravitational pull on a paperclip. This highlights how weak gravity is compared to other forces. Speaking of powerful forces, the strong nuclear force is astonishingly intense, about 10 to the 38 times stronger than gravity. That's like saying it's 100 trillion times more powerful. It's what keeps atomic nuclei intact, which is fundamental to everything around us. Now, on a different scale, the sun is like a gigantic nuclear factory. It converts around 600 million tons of hydrogen into helium every second through nuclear fusion. This process releases enormous amounts of energy, which travels all the way to Earth as light and heat, fueling life and driving our climate. And finally, there's the quantum realm, where things get even more fascinating. Particles affected by the weak force can spontaneously change their identity, or flavor. For example, neutrons can transform into protons. This ability to change identity is unique to the weak force and plays a crucial role in some of the universe's most fundamental processes. All these points show how different forces operate at different scales and intensities, shaping everything from the tiniest particles to the vast cosmos. Thank you so much for joining me today. As we wrap up, I want to emphasize that more mass means more matter, which is a simple yet powerful idea at the core of our universe. Throughout this presentation, we've explored how mass and energy are interconnected, a concept famously captured by Einstein's equation, E=mc². This equation reminds us that even a small amount of matter contains an enormous amount of energy, highlighting how fundamental and energetic matter truly is. Our journey through gravity, electromagnetism, and nuclear forces has shown us a universe full of complex interactions, each force playing a critical role in shaping everything around us. These forces open up endless possibilities for discovery, reminding us that the universe is a vast, intricate tapestry waiting to be understood further. If you found this presentation interesting, I encourage you to like, share, and comment. And don't forget to subscribe to our channel for more insights into space science. Thanks again for exploring the universe with me today.